when we do double integral in polar coordinate, we consider those polar rectangle. How do polar rectangle look like? So for example, over here, we have this and this. They don't look like rectangle to you. However, in polar coordinate, they are called polar rectangle. Why? Because think about rectangle in the Cartesian coordinate system. The x and y coordinate are bounded by constants, right? And in polar coordinate, we have r and theta. For this two region, r here is bounded by two constants, and then theta, the second coordinate, is also bounded by two constants. So this kind of region, we call them polar rectangle. Okay? So keep that in mind. Those are called polar rectangles. Okay. The first and the second coordinate are bounded by constant. And when we do double integral over polar rectangle, the way we do it is we divide the formula last time. And we first use Riemann sum, and then we come up with a formula. The way we do it here is like that. So in Cartesian coordinate is the integral, the double integral of the function, okay, and then dA over a region R, okay. And now we can write this in polar coordinate. So remember, x is r cosine theta, y is r sine theta, and then the dA over here, think about that as a small change in the area there. Replace this by r dr d theta. R d theta, think about it as this length of this arc, and then dr here, think about it like that. Think about that as kind of like a rectangle. So we place dA here by r dr d theta, and then the r here change from a to b, theta change from alpha to beta, and then you can set up the integral, and that's how we do double integral in polar coordinate. Okay, remember this dA here is being replaced by this r dr d theta, and then we did example. We finished the example 1 and example 2. And now we get to this one here. Now, before we jump into this, maybe I will give you a review for polar coordinate about this topic over here. So what do we do? Okay. So first of all, do you guys remember how do we, so suppose we have a circle, and if we try to find this segment of the circle, what will be the area of this segment? Suppose that the radius here is r, and this center angle here is theta. What is this area over here? Anyone? Well, you can do this. You can do pi r square. That's for the whole circle, right? But then the bigger the center angle, the bigger this area of the segment. And it is proportional to this center angle. The whole circle corresponds to the center angle to be 2 pi. So this one here, this segment is going to take theta over 2 pi of the whole circle. Okay. Now, when you simplify this, that is going to be 1/2 r square theta. So that is the area of the segment over here. Now, another way to actually remember this, or try to think about this is actually can be divided into small segment, and each segment is about like a triangle. And when you add up all those segments, you add up the base, and then think about this like a triangle. So what happened over here is the base of this is this part here, the R. If this is R, this is data. This arc length here will be R times data. So this, let me do this. So this one over here is going to be R times data. And for triangle is 1/2 base times height. Now think about the height here is the R. So it's going to be 1/2 R times R data. Again, you get 1/2 R squared data. So this is the area of this segment over here. Okay, question? All right, so if you remember this, now what happened over here is we're going to think about the area that is going to be, now let's try this. So in this polar coordinate system, we have the pole, and this is a polar axis, and we get this polar curve over here. And this polar curve is going to correspond to this right here is data equal to alpha. And then the other way here is data equal to beta. Okay. And if you try to find out this area over here, even you this polar curve is R equal to whatever, this is a function of data, G of data, say. Okay. Now, how do we find this area that is bounded by this polar curve and this two ray over here? Anybody remember this? Now, at that time, we actually divide that into small segment. Okay, just like in calculus, we always divide things up into small segment. And each segment over here is almost like a part of a sector of a circle. So each segment here, think about almost can be approximated by something like this, like a sector of a circle. And think about, because the R here doesn't change much in this small segment, so think about the R here and the R here are about equal, okay, in this segment. Then you can approximate this segment here by a sector of a circle, something like this. And now we can concentrate on one sector. For each sector, it's going to be, the area is going to be what? 1/2, right? And then R square. And then the angle that is, this one here is facing, this one facing here is the small change in data, right? In this segment here, there's a small change in data. So let's think about this one over here. That's the D data, right? D data, like this. So D data, like that. That's for one segment, okay? Now, and then we use integral to sum this up. So we sum that up. And data here go from alpha to beta. Then this is the area that is enclosed by this polar curve. And this two right here. Data equal to alpha, data equal to beta. So that was the formula that we had. So that was this case. Okay, so that was kind of toward the end of Math 110B in chapter 10. Okay. Now, what about if we have polar curve like this one over here? Like this one over here? Okay, you see down here? So you have this polar curve. This is the, okay, let me draw this over here. So this is the pole, and this is the polar axis. And you have one polar curve that is further away from the pole, And then you have another polar curve over here, like this. Okay. Let's see. Let's label them. This one over here is a R1. Okay, this is R1. And that's equal to a function of data. Let's call that G of data. And then for the other polar curve here, let's label this. So we call this R2. Okay, let's give it, distinguish that as R2. And that's equal to a function of data, let's say f of data. Okay. Now what happened here is, if you try to find out when data change from alpha to beta, this part, the area of this part of the region, then what should we do? Any idea? We know this, right? How can you relate this one with this one? This part of the region, how is that related to a region like this? What do you think? Yeah. So for this one here, it's going to be this big sector, subtract this small sector over here, right? Okay. So like the big piece of the pie and subtract the small piece of pie, right? So we can take this, the first one, you substitute R2 in it, and then subtract the second one, you subtract R1 in it, and when you subtract them, you will get the area, right? Okay, so let's write that down. So the area over here is equal to the integral. Both of them have 1/2. The first one is, the outer one is R2, or you can put O for out, okay? R2, okay. And this is the outer. And you square that, right? Okay. And you have this D data here. This one corresponds to the area of the sector, this big sector over here, right? And then you're going to subtract the inner one. In this case, it's R1. Here, square. So the difference of this sector and this sector is the area over here. Data here change from, looks like here it changed from what? Alpha to beta. So we'll have alpha to beta. So this is the formula that we have before. Okay, let me label that. This one here, the R1 here, is the inner one. Okay, like that. So that was what we learned in calculus 2. Okay, when we have a region that's bounded by two polar curves, okay, then you take this, you use this formula over here. So looking at this picture, this one here is this case over here. Okay, just like that. Okay. Any question about this? Okay. All right. So, okay. Now what do we do here? Okay. Now let's look at this one over here. When we try to find this region over here, it's going to be this one over here. We did this one before, right? And we also did this one. We talked about this one already. When we talk about double integral of 1 over a region is equal to the value. Did we talk about this before? Okay, let me double check. So if continue a polar curve, then this. Okay, good. Okay. So the way that we do this double integral over polar coordinate, okay, then just like before, when we take this double integral over, is it kind of small? Okay, then make it bigger. This double integral over this region D over here, then you're going to replace this x over here by, this is the x, right? And this is the y. So we replace this x by r cosine theta, and then y here by r sine theta. And again, the dA over here, you replace r dr d theta. Okay. Now, but this time, what happened? The r over here is not going to change from a constant to a constant. Because as you can see here, what happened to the r? The r here is not a constant, right? So as the data here increase, you see the r here is changing. Sometimes bigger, sometimes smaller. And r here is a function of data, right? R here is, in this case, is h1 of data. Okay, so this is the inner one. Think about this as the inner one, inner r. Okay, and it's a function of data. And so r change from this, and to this. This is the outer. Okay, like that. So when we have this integral over here, the r over here is going to change from this. This one here is the inner one, right? Okay, and to, well, I think the inner one I use blue for that. This inner r, okay, and then to this outer r, right? So r change from this to this. And looking at this picture, actually this picture also worked, okay? So r here change from this to this. So if I change this to h1 data, this is this one here, h2 data, and this is exactly the formula over here, okay? r change from this inner one to this outer one. And then what about data? Data here change from alpha to beta, from a constant to a constant. So just like that. So you can actually read this from the picture. Okay, you can set that up from the picture. Okay. Over here, also talk about, in particular, if you take this function here to be this constant function 1, and you take h1 of data to be 0, h2 of data to be h of data, what does it mean? Okay, let's try to graph this. So yeah, there's polar on this polar plane. So I have 0 here, polar axis. h1 of data equal to 0, which means the inner one is going to be, think about this inner polar curve. It's just a single dot here at the pole, okay? And then h2 of data equal h data, then you're going to get like this. This is h of data, okay, r equal to this, okay? Then what happens if you use this formula, okay, use this formula over here, you're going to replace this function here by 1. So you have this 1 over here by 1, that's 1, and integrate this constant function 1 over this region, okay, over this region over here. And what should we get? When you integrate constant function 1 over region, should that be equal to the area of this region? Right? Okay. So that should be the area of the region. Think about this piece of cake, right? So this is like a piece of cake, but this one here has the height to be 1. So when you use this base area times 1, that's a volume. Remember, this double integral here corresponds to the volume. Okay, think about that as the volume. This one here is the volume of the double integral correspond to volume. Okay, so this piece of cake has the height to be 1. So base area times 1, then that's also in quantity that's equal to the base area over here, right? Okay, and now this is 1, and now on this side over here, okay, you're going to have this is 1, right? The function is still 1, right? So you can put a 1 there if you want, okay? So you can have a 1, and then you're going to replace this dA over here by dA by R drd data, okay? And the R here changed from what? Well, the R here, the smallest R, right, is at the origin, right? So R here will change from 0 and all the way to this outer one. So R change from 0 to this outer, so 0 to HL data, okay? And what about data? Data change from alpha to beta, okay? So then we have this. And when we evaluate this integral here, we will do the inner integral first. So for this inner integral over here, when we do the inner integral with respect to R, the antiderivative R here is R squared over 2, right? It's R squared over 2. And then R change from 0 to HL data, okay? And now you substitute that in, okay? You get this, okay? This one here agree with the formula that we have. Why? Because what is HL data? It is R, right? HL data R. So it's 1/2 R squared d data. Data go from alpha to beta. So it is the same formula that we got over here, right? It's the same formula, okay? Okay. Now let's try another example, okay? I feel like polar coordinate, maybe some of you might forget a little bit, so it might take some time to come back, okay? So this one over here is double integral to find the area enclosed by one loop of this 4-leaved rose, okay? Now, actually in my 110B, we just talked about this like last time, okay? This is a 4-leaf rose, okay? We graph it, okay? And we just interested in to find the area enclosed by one loop. You don't need to use double integral to do this. However, today, let's see if we can use double integral to do this, right? So in 110B, we actually using just a single integral to find this area, right? Okay. So how do we do this? If I try to find this area, first I will need to think about this one loop of rows. We want to find out the corresponding alpha and beta. So how do we do that? You can actually set R equal to 0. So you can solve cosine 2 data equal to 0, and then you find out data actually have different number, and this 2 that corresponding to this paddle over here is data equal to negative power 4, and here data equal to power 4. Okay. All right. So this is alpha. This is beta. And the R here. Well, what happened to the R? R here is going to. Okay. So in order for you to see the R, it's better that you can try to draw a segment like this. Okay, start from the origin, point to this outer. Okay, so the R over here, you can see that R go from 0 all the way to this outer one. The boundary here is this R equal to cosine 2 data. So R change from 0 to cosine 2 data. Okay, from here to here. Okay. This one here, R change from R1 to R2. This one over here, R change from 0 to cosine 2 data. Okay. Now, without looking at the book, let's see if we can find this area over here by setting up the integral. Okay, so how do we do this? Well, finding this area over here, well, imagine them over this paddle over here. You have a solid that has height to be 1. Okay, so height to be 1. So think about that would be like a building or some Lego. Okay, above this, it's going to have height to be 1. So think about in 3D, you have this paddle, but it's going to elevate by 1. And think about the value for that 3D paddle has height to be 1. Okay, then because the height to be 1, then the value of that is going to be equal to this area, the base area. Okay, so we can find this over here. So this base area, let's call that, this is like the base area, is this paddle. Okay, then that is equal to the double integral of 1. So it has to be height 1. If it's not 1, then it's not equal to the base area. The value is not equal to base area, right? So double integral of the function 1 and then dA. And the A here is this region D. Okay, so this region, let's label that D. Okay, call this region over here D. Okay. Right. So that is equal to, this is the value of a solid has height equal to 1 and with this base area. And in quantity, they are equals. Okay. Now we can use this polar coordinate to do that. What do we do? The 1 there is not that, it doesn't matter if it's 1. And what do we replace this dA here by? We place the dA over here by what? R, dr, d data, right? Okay. Now we need to figure out the R here change from what to what. Let's see the R change from, you see this one here is dr. Okay. R change from what to what? Looking at the picture here. 0 to cosine 2 theta, right? See, looking at this, the R start from here, right? And then to here. So R change from 0 to cosine 2 theta. So let's write that down. So R change from 0 to cosine of 2 theta. Okay, this is. What about theta? Theta change from what to what? It has to from small to big. Yes, theta change from negative power 4 to power 4. Yeah, you got it. Good job. Okay. So that is negative power 4 to power 4, right? So from this to this. Okay. So we set up this. Okay. Now, how do we evaluate this? Let's continue. Okay. So after this, what should we do? You do the inner integral first, right? Okay. So let's find the inner integral. This inner integral over here. What's anti-duality of R with respect to R? Yes, it is R squared over 2, right? And then after that, you will just have the R here change from 0 to cosine of 2 theta, right? Okay. Like that. Then after that, let's see what should we do. Let's finish this one example. Okay, so I can actually bring out the 1/2, right? So the 1/2, so you have what? Cosine of 2 theta square, and subtracting 0, then it doesn't matter if we're subtracting 0. So we have this, and then you have this d theta over here. Theta change from negative power of 4 to positive power of 4, right? Okay. Okay. I think I should maybe put a parenthesis here on the 2 theta to avoid ambiguous, right? Okay. That how do you find this integral without using computer? What was the integration method that you would like to use? If it's when the exponent on cosine here is even, think about which angle formula. Half angle formula. Yes, very good. Okay, do you guys remember the half angle formula? Okay, so half angle formula with this cosine of square of x, that's equal to what? 1/2 1 plus, right? Cosine of what? 2x. Yes, good. If it's sine square of x, that is 1/2 what? 1 minus. Good job. Okay, remember. Okay, that was the half angle formula, right? I think we used it again and again in 110B. Okay, so calculus 2. So over here, when this exponent for cosine here is even, we think about use a half angle formula. So using half angle formula, this one here is going to become 1/2 of 1 plus cosine of what? 4 theta, right? Okay. Now after that, you can find antiderivative, right? So 1/2 times 1/2 is 1/4. Okay, and antiderivative of 1 is going to be theta. Okay, and what's antiderivative of cosine of 4 theta with respect to theta? Sine of 4 theta divided by 4. Yes, you got it. Good job. Okay, so if we sine of 4 theta divided by 4, and now finally you're going to substitute theta to be negative power of 4 to power of 4. Actually, you can cut your word in half by using symmetry, right? Do you notice that in this case, this upper part of the pedal and the lower part of the pedal, they're symmetric, right? So you can actually go from 0 to power of 4 and you double it, right? You will still get the result. But in any case, when you do the calculation over here, okay, yeah, so that's what they got. It is pi over 8. Okay, so do the calculation, the result here should be pi over 8. So what is this? This is the area of the pedal. Okay, so after all this work, we found out the area of this pedal is pi over 8. And that's also equal to the volume of the solid have this as the base and 1 as the height. So for the whole rows here, what will be the area? Is this pi over 8? Pi half. Yeah, pi over 2. So this whole rows here will have pi over 2 as the area. Okay, good job. Now, this is how you do this using double integral. But remember, we actually did this without double integral in calculus 2. But this is just another way to do it. Okay. Okay, the next example over here, we're trying to find, maybe ask someone to read this. Okay, can I ask, who want to read this? Hongzhen? Sorry, Hongzhen. give you guys some participation opportunity. Hongzhen, can you read this? Here. Okay, very good. Okay. So we have this paraboloid, z equal x squared plus y squared. And how does it look like? Let's see. It look like this. Okay. So if you try to graph it, this is the paraboloid. Okay. Look like just look like this. Okay. Okay. And then above this xy plane and inside the cylinder, x squared plus y squared equal 2x. Okay, let's label this. So I'm going to label this. This one here is d equal to x squared plus y squared. And then for the other one over here, okay, this one here, this cylinder is x squared plus, make it bigger, x squared plus y squared equal to 2x, that cylinder. Okay, so you have this paraboloid and you have this cylinder. Okay, imagine the cylinder here go up and down like that. Okay. Now, what are we looking for? We're looking for the value of the solid that is going to be under this paraboloid. So it has to be below the paraboloid. So there will be this part here. And then above this XY plane and inside the cylinder. So we're basically looking for, what are we looking for? So this yellow work. Okay, I'm going to use green, see if it works. Okay, we're looking for this. Oh, the green doesn't. Let me use purple. Purple is not. Okay, pink. It's not that good, but anyway, let's do the work. Okay, so I'm looking for this part of the solid. Okay, this part of the solid right there. Okay, so under the paraboloid, above the xy plane, and inside the cylinder. Okay, so we're going to, when you find value, you're going to set up a double integral. Okay, let's try to do this. So we're going to set up the double integral. Without looking at the book, let's see if we can do it. Okay, so it's a double integral of a function. Well, what is that function? Well, you have to think about the height, right? So what's the height of this, right? So the ceiling is going to be this. The ceiling is going to be this z equal x squared plus y squared, right? And this is, think about that as a function of x and y. Okay. So the function that we integrate with, okay, this is the ceiling. Okay, it's going to be x squared plus y squared over here. So let's put that down. So that will be x squared plus y squared. Okay, and then we integrate this function, okay, over a region down on the xy plane. Down on the xy plane, that's the region. Okay, how do you get this region? Because you complete the square over here. Okay, so if you complete the square, this one here is x squared minus 2x, and then you think about what number to add here, plus y squared equal to what? Okay, to complete the square, you take, what do? We take half this coefficient, so it is -1, and you square and put it here, that's 1. Okay, you put a 1 there to complete the square. You add 1 on this side, you add 1 on the other side. So after that, it's going to turn into this. So you got x minus 1 square plus y square equal to 1. That's it. That is the same equation, except this one here is more in standard form. Okay. So from this, once you complete the square of this, you got that. And you know that on the xy plane, okay, then it's going to correspond to this circle. Okay. So, and the inside of the circle, this region is what happened, is this integral is going to be integrated over. So if I put this dA, then the region that you integrate over is this region D, this region here D. Okay. So far, okay? Hey. All right. Okay, let's do it. Okay. So now that's equal to double integral. Well, remember the function above here is x squared plus y squared, right? And now, because this region over here is more in a circular shape, right? So you think about using polar coordinate, okay? Using polar coordinate. Okay, so actually I shouldn't do this one. Okay, so think about using polar coordinate because the shape of this region. So in polar coordinate, we can represent this region here. What is it? Okay, this region over here is, what's the equation for this circle? Now, if you remember from 110b, this circle over here, that circle, okay, let me try that. Okay, so you have this pole over here, and then this polar axis. And for this circle over here, with radius to be 1, okay, then that circle, the diameter of this is going to be 2. And if you can remember from 110b, the equation of this circle is going to be, anyone remember from 110b? Do you remember equation for this circle? What does R equal to? R equal to what? Don't remember? Okay, so actually I was trying to give you guys a quick review, okay? So it was like this, okay, let me give you a quick review. So it was like this, okay? And if the circle is going to be centered at the polar axis, then whatever this diameter over here, the diameter over here, let's call that, then suppose this is a 5, the diameter is 5, then the equation for this circle here is going to be R equal to 5 times cosine of theta. Okay. And if the circle is like this, with the center here over here, okay, then say the diameter here is 5, then the equation for this circle is R equal to 5 times sine of theta. Okay, so I can give you guys some material to look at if you forget about this. Okay, so in this case, this is a circle and the center here is at this polar axis. Then R is equal to what? 2 times cosine of theta. Okay, 2 times cosine theta. That's the equation for this circle. Okay, so therefore now we expect this as in polar coordinate. That's the equation for the circle. Now we're trying to express this region. Okay, let's try to think about R here change from what to what, and theta change from what to what. Okay, so R is going to change from what to what. Okay, it might be helpful to try to draw some segment like this, right? So R is going to start at the start at 0, right? So it's going to start from 0 and end it at where? Cosine 2 cosine theta, right? So that will be 2 cosine theta. Okay, so R changed from this to this. Okay, and what happened to theta? Theta changed from what to what? If you complete this, theta changed from it's negative power 2 to pi over 2. when you do this, this is negative pi over 2 to pi over 2. Okay. And how do you do this? Well, how can you find out this data? You can set 2 cosine data equal to 0. So that way the radius, right? If you try to find out when will this be at the pole, you're going to set r equal to 0. So when you set r equal to 0, you get what? 0 equal to 2 cosine of data, right? Solving this, you get cosine data equal to 0. What does cosine data equal to 0? Data equal to what? Pi over 2, right? And what else? Negative pi over 2, right? So it's going to be at the pole when data equal negative pi over 2 and pi over 2. So here we'll have data go from negative pi over 2 to pi over 2. So now we have this, then we should be able to continue with this integral. Okay, I'm going to make this on the other side. Okay. Okay, now let's think about it. Because this region here is like in a circular shape, so I think about using polar coordinate. That will be equal to the double integral. What do you notice about, if I change, okay, first I'm going to change this dA over here by r dr d data. Then will be double integral with respect to r and data. Let's express x squared plus y squared. Let's relate this with r or data. Okay, do you guys remember x squared plus y squared? How is it related to r? Remember this? This is x, this is y, and this is r. How is x squared plus y squared related to r? Yeah, that's equal to r squared, right? So remember, this one here is this r squared. So this r squared over here, okay? Now we just need to figure out the r here change from what to what. R change from, well, we already put it here, right? R change from 0 to 2 cosine data. So let's put it down. So that will be 0 to 2 cosine data, right? And then what happened to data? Data change from negative pi over 2 to pi over 2. So we put it down. Negative pi over 2 to pi over 2. Now we set up the integral. Okay. A little bit messy. So hard. It's a little bit hard to see, right? But the most important part here is you're going to be able to set up the integral. Okay, so that's the integral over here. Okay, notice r squared times r, this should be r cubed. Okay, so that should be r cubed over here. Then after that, all you have to do is just, so once you have that, you can just follow this. Again, it uses a half angle formula. When the exponent on cosine here is even, think about use a half angle formula. Okay. Okay, and then you should be able to get the result here. Okay.